Okay, physics party people, here's our video on applications of torque. So, we have previously looked at torque in more of a fundamental capacity, basically, of just saying, okay, a force further out from a wheel gets a larger torque, or a bigger torque. A bigger force means a larger torque, or as you go closer and closer to perpendicular um, with the same force, same radius, perpendicular is the biggest torque, whereas at an angle is not the biggest torque on that. Just as a quick reminder of everything that we have talked about up to this point, if we are looking at an individual torque, so I'm just going to label that as torque for an individual object, we can calculate that by taking r f sine theta, where we have, let's say we have some pivot point there. If that's our radius and we have some sort of force here, so r, f, and then theta is the angle between the two, where 90 degrees is the most favorable angle for having a large torque. That's for an individual torque. But if we have more than one, or if we want to relate the torque or torques acting on an object to its motion, we have the sum of the torques. The sum of the torques is equal to I alpha, which, right, is very similar to our sum of the forces expression. It's just all the positive ones, and then you subtract all of the torques in the negative direction. And there's our expression there. So all of a sudden we can relate what's the thing that's rotating, how quickly is it changing its rotation based on the torques that are present, everything that's helping it move faster and everything that's causing it to move slower or slow it down. Where I is that rotational inertia. Remember everything that we did as far as relating rotational inertia to a radius, everything like that. So let's take a look at how this torque expression, now remember this, sum of the torques we might also call net torque. And this would actually be more of how you would see this written out as being the net torque acting on an object. And that just means you take everything in a positive direction and then you subtract everything that's acting in the negative direction to find the net torque. Okay, let's take a look at some examples of how this might show up. But first, I just want to remind us of a principle and of a system type that we did all the way back in Unit 2 for forces. And this is called an Atwood machine. All right, it's two blocks connected to each other over a pulley. And for it to be a straight up, just normal Atwood machine, the pulley has to be massless and frictionless. Now, if the pulley has mass and or has friction, that's when we get into kind of the Unit 7 stuff, which I'll show you how to work with in just a moment. Okay, so we have this pulley with two masses hanging over it as shown of 0.8 kilograms and 0.3 kilograms. I'm just going to pause right here. If we released from rest, which direction does it rotate? Toward the heavier one. So remember, when something is going to move one way, we just call that positive. All right, so if we look at our system as being just this string, right? For Atwood machines, we do the sum of the forces, but it's on the system. Everything that goes along the string. So we have ma, mass times acceleration, is equal to, and then all the positive forces, which is gravity pulling block 1 down, and then subtract all the negative direction forces, which is gravity pulling block 2 down, which is holding us back. All right, remember this mass here. This is all the mass that accelerates, which would be both of our blocks. So we have to take mass total times that acceleration, mass total acceleration. Force of gravity is mg, and that's for block 1. Force of gravity 2 is mg for block 2. All right, we can start to plug in some numbers here. So our total mass, well, we have a 0.8 and a 0.3, so 1.1. And our acceleration is what we're being asked to find the acceleration of the system. Mass 1 is 0.8 times 10. Mass 2 is 0.3 times g is 10. All right, so all of a sudden we have 1.1 A is equal to 8 minus 3. And I hope you can do 8 minus 3 in your head. That would, by this point in your schooling career, you should be able to do that. Divide both sides by 1.1. And 5 over 1.1, I get 4.55 meters per second squared is our acceleration rounded to 3 sig figs. Okay, so there's our normal Atwood machine. Now, let's look at problem 2. Take the same setup and masses, so it's still the 0.8 and the 0.3, but now the pulley is not massless. The pulley has a radius of 12 centimeters. The tension in the string attached to block M1 is 5.6 newtons. Okay. Before we get too far into solving the problems, let's just take a quick little look at this all in terms of what's different. Well, we've got this pulley here, and we have this string that's attached to block M1. And there's some amount of tension in this string, which I'll just call tension 1. Now, this string does continue over the pulley. That's the contact point, or the final contact point with the pulley, and then continues down to the point where it intersects, or it's connected to block 2 over here. In block 2, we have a tension labeled T2. Now, what we've been able to do in the past is say that, because of Newton's third law, tension 1 equals tension 2. However, that is no longer true. If the pulley is not massless, right, we decided that it's going to rotate in that counterclockwise direction. So if it's rotating this way, then tension 2, as tension 2 is going up, what does tension 2 pull? Well, tension 2 is just responsible for pulling. Sorry, my pen's having a hard time here. Tension 2 is responsible for holding onto mass 2 and accelerating mass 2. However, wow, the pen is really struggling today. However, even though tension 2 is only responsible for holding on to and pulling up mass 2, tension 1 over here is responsible for not just mass 2, but also the pulley. And since the pulley has mass, so tension 1 is going to have to be bigger than tension 2 now. We can't say Newton's third law because Newton's third law only works when there's no other forces that are interacting within the system. And in this case, there is, because there's the contact between the pulley and the string. There's no way that we can just cite Newton's third and say there aren't any other forces, because now there are. When the pulley is not massless, tension 1 has to pull both M2 and the pulley, whereas tension 2 just pulls the pulley, just pulls M2. So all of a sudden, we can't really look at the system as easily anymore because tension 1 and tension 2 are different from each other. Okay, so this question here is asking us determine the acceleration of the blocks. Zooming back in here. Because we can't look at the system too well on its own, we're going to have to look at block 1 kind of on its own. We're going to have to look at the pulley kind of on its own, and then block 2 kind of on its own. Now, we know that block 1 and block 2, since they're connected by the same string, they will have the same accelerations, right? Acceleration 1 and acceleration 2 have to be the same. And we can also say that that has to be equal to the tangential acceleration of the pulley, because that's sliding along with the string. But with the pulley, right, it's rotating, which means that for the pulley, we care more about alpha than we do about A. But we can relate, because we know this A here and this, the A here and the alpha up there, because we know those two things have to correspond to each other, we can get a little bit more information about some of those. So just that as a reference, because all the forces are kind of different from each other, it's really hard to look at the system as a whole. So instead, we'll break it down piece by piece and just look at all the things acting on each individual piece of the system. Okay, now let's look over here. Determine the acceleration of the blocks. Well, the acceleration of the blocks, well, we know mass 1 has Fg1 weighing down on it and Ft1 pulling up. Block 2, it's very similar for block 2 over here. For block 2, and my pen is not responding, I apologize. For block 2, well, mass 2, it has gravity 2 down, and it has tension 2 up. So they're very similar free body diagrams over here. Gravity 2, oh my goodness sakes. Sorry, thanks for bearing with my technical difficulties on my pen here. Gravity 2 down, tension 2 up. Now we know force of gravity on each of those. That's just given by the mass. We know Ft1 because we're told the tension in the string attached to block M1 is 5.6 newtons. Since we know both of these pieces of information, I'm going to say to solve this problem, to determine A, this acceleration, let's use block 1 because we know more information about it. So I'm going to say acceleration of block 1. We will find that, which we can do by, right, we have forces and we want acceleration, the sum of the forces on block 1. So we have mass of 1 times acceleration. So this mass of block 1 times the acceleration here. Well, gravity is pulling it down and tension is holding it back. If you remember over here, that's because block 1 is going down, is why I'm calling gravity the positive force. All right, so we have M1A is equal to, gravity is mg for block 1, force of tension, we're just given that number. And we might as well start, or after this, we'll have the ability to start plugging in all the numbers just now that we broke down force of gravity here. So mass 1, if you remember, has a mass of 0.8 times our acceleration A. mg, well, that's 0.8 times 10, so 8 minus, and then Ft1 is 5.6 newtons. So I can say acceleration, or 0.8A is equal to, 2.4. Divide both sides by 0.8, and we get acceleration of 3 meters per second squared. All right, so there's our acceleration of block 1. And since block 1 is attached to block 2, they'll have the same acceleration. So we can say that 3 meters per second squared is the acceleration of both blocks, even though we just did the math for block 1. Part B, determine the tension in the string attached to block M2. So now we're looking for this tension here that we didn't have earlier. Okay, well, if we're looking for a force attached to block M2, really the best way we know how to set that up is the sum of the forces. But now we can look at block 2 since that's the force that we're looking at here. By the way, tension 2 acts on 2 objects, block 2 and the pulley. But we haven't done anything with the rotation of the pulley yet. And usually if you can do forces, it's easier than torques. So I'm going to say if you can do an object that is moving straight in an axis as opposed to rotating, do the forces first because we're more familiar with those and there's less things that can go wrong just mathematically speaking. So let's do this. Sum of the forces is MA for block 2. Now for block 2, it's accelerating upwards, so force of tension 2 is our positive force. Gravity is holding us back, so F minus Fg2. All right, M2A. Force of tension 2, that's what we don't know yet. Minus, and then force of gravity is mg for block 2. All right, we can plug some numbers in now. Mass 2 is 0.3. Our acceleration, well, we can say it's the same as block 1 that we found in that previous part of the problem because they're attached to the same string, so they have to accelerate at the same rate. Okay, ft2 minus, and that's what we're looking for, 0.3 times 10. All right, so we can say over here 0.9 equals force of tension on block 2 minus 3. We can add 3 to both sides. Okay, so tension in the string attached to block 2, 3.9 newtons. All right, there we go. There's tension to block 2. Part C now. What is the angular acceleration of the pulley? Well, angular acceleration of the pulley. There's a couple of ways that you could go about this. Now, one of them is similar to what we've been looking at, where we see alpha show up on our equation sheet. Angular acceleration, right, we're looking for alpha. And one of the places that we see alpha pop up on the equation sheet is the sum of the torques is equal to I alpha, which is, right, that'd be the torque of tension 1 minus torque of tension 2, because we have the tension attached to block 1 is kind of pulling our mass, or is pulling our pulley forward in that axis, and then the torque of the string, the torque of tension attached to block 2 is kind of holding us back. Here's the problem with this, because right, we could do RF sine theta, and we know the geometry for theta. We know the force of tension on each of these, and we are told, if you look at the top of the problem, we're told the radius of this wheel also. So we know all those pieces of information for tension, or for torque 1, torque 2. What we don't know yet is I. So we don't have access to this method quite yet because we don't know the rotational inertia of the pulley. And we're not given an equation to find I. We're not told its mass at all. We're just told that it's not massless. So we have no way to get I yet. So when we solve for angular acceleration, we're actually going to look back at what have we done before. And we found acceleration. Is there a way that we can relate acceleration to alpha? Well, yes, there sure is. Now remember, our access point to relating these is omega, right? Omega times r. Omega times r is our velocity. So if we turn this into acceleration, right, the linear is equal to the angular times r. Here we go. Because we can now say alpha is equal to A over R. And acceleration, which we found in part A of this, the acceleration of our system linearly was 3 meters per second squared. Radius of this wheel is 0.12 meters because it says 12 centimeters. 0.12 meters. And my pen is now just pretty much completely turned off. So our radius of our wheel, 12 centimeters, 0.12 meters. Plug that into your calculator. And we get alpha is equal to 25 radians per second squared. Okay, there's our angular acceleration of our system here. All right, so we're almost done with this problem. Last but not least is determine the rotational inertia of the pulley. Well, remember this approach here that we were talking about that we didn't have I for to solve for alpha? Well, now we have alpha, so we can solve for I. So let's do that. So we can say the sum of the torques on the pulley is equal to I alpha, and then torque of tension 1 minus torque of tension 2. All right, well, I, we don't know. Alpha, we do know, but I'm just going to leave it there while we get some other expressions written down and plugged in for all these torques. All right, torque 1, R, and then F of tension 1, sine of theta for that, sine of theta. And then torque of tension 2, right, we have R, F, sine of theta, but that's for the second one. This is for the first one. And FT2 is that one. All right, well, we can start plugging in numbers now. Alpha, we said, was 25 is equal to, and then remember R, I'm not just going to automatically plug in the radius of the wheel. I want to make sure that the torque is acting at that point that we know of. Well, if you look at, here's the contact point of the string. You have to go all the way from the edge of the disc or the edge of the pulley to the center of the pulley, which is the entire radius. Okay, so that's what we'd expect. Radiuses of the pulley, and the angle between the radius and the force, well, those are perpendicular. It's 90 degrees. Okay, so on top of saying R is just 0.12 with that 12 centimeters, and then FT1, we were told that that was 5.6 newtons. We can also say sine of theta 1 will go away to 1 because it's at 90 degrees. Same with sine of theta 2. They're at their maximum that they could ever be at 90 degrees. They're perpendicular to each other. So sine of thetas will just go away because they're equal to 1. So then minus, and then R is 0.12. And then FT2, 3.9 newtons is what we solved for in that case. So now I can plug some stuff into my calculator, 25I, and then everything on the right side of this equation, 0.12 times 5.6 minus 0.12 times 3.9. On the right side, I get 0.204. So then I divide both sides by 25. I get my rotational inertia is equal to 0.00816 kilogram meter squared. If my pen lets me write units on this, there we go. There's our rotational inertia of our wheel. All right, highly encourage you pause this video, just take a moment and reflect back. What did we do? How did we know to do it? And especially over here, what I had mentioned kind of toward the beginning, where we separated out. When you have some things rotating and some things moving linearly, you really can't treat the system as a whole anymore. So you kind of have to look at one piece of information at a time, one moving object. Just because we have things rotating and things moving. So you don't know whether to use torques or forces if you have everything going at the same time. So decide what you're looking at, and that will help you decide whether you're using torques or forces based on whether it's rotating or not. Okay, moving on to our next problem here. So number 3, we've got an 8 kilogram mass unwrapping a rope that's been wrapped around a pulley many times. And this is something that I forgot to mention, as the string pulls down, it unwinds and it spins the pulley. has a mass of 4 kilograms, radius 20 centimeters, with a rotational inertia of 0.08 kilogram meters squared. The tension in the string is 13.3 newtons. Determine the following. All right, A is the acceleration of the block. The acceleration of the block. Okay. Well, if we're looking at acceleration of the block, so this is kind of similar to what we had before. We have the block is kind of one piece of this system, and then the pulley is kind of the other piece of this system. And since one moves linearly and the other one rotates, we can't really treat them together. So we're going to just have to take this one at a time. So the sum of the forces on the block, because it's moving linearly, so we use sum of the forces, equals MA equals, and if we take a quick peek at if we were to make a free body diagram on this block, well, we've got gravity is pulling it down, force of gravity, and we've got the tension in that string that's pulling it up. All right, so, and it's moving down, as we can see by this arrow here. So gravity will be the positive force, and then tension is the force in that negative direction that's holding it back, restraining its movement. All right, well, mass is 8. Acceleration is what we want to know. Force of gravity is m times g, 8 times 10, minus the tension in this string, 13.3 newtons. 13.3 newtons on that is the tension in the string. Okay, so this is actually pretty straightforward. 8 times A is 80 minus our tension, 13.3. If my pen decides to work. All right, 13.3. Okay, so if we take 80 minus 13.3, we'd get 66.7 is equal to 8 times A. It's equal to 8 times A. So if we solve that, divide both sides by 8. Sorry, my pen keeps not writing. Thank you for bearing with me on this. I know this video is a little bit longer than it had to be because of those technical problems. So 66.7 divided by 8, and I get acceleration is 8.34. 8.34 meters per second squared. All right, and the fact that that's less than gravity is good because that means that it's not falling faster than things are physically allowed to fall. All right, part B, angular acceleration of the pulley. Now, if this were an AP test or a test or something like that, I would really want you to use the easy way to do this. You have A, find alpha. Easy, especially if you have a radius there. Instead, what I'm going to ask is, just because we're learning and we're practicing how to do this, just know that that's the easier option. I just want to practice setting up another net torque expression. So let's take this as the sum of the torques, because we're talking about the pulley now. So we're going one object at a time, and this object happens to be rotating, so equals I alpha. And then the only force that is exerting a torque on this wheel is the torque of tension. So we can say the torque of tension here. Now if we zoom in on our wheel, well, there's the center and there's the contact point. So the radius, that will be equivalent to the radius of the wheel. And the force goes down below, so that's at a 90-degree angle. Okay, so we can just kind of say that everything is as expected here in this RF sine theta, but since they're perpendicular, sine theta does not impact this. It equals 1. All right, so I, our rotational inertia, we're told in the problem 0.08 kilogram meter squared. Alpha is what we're looking to find. It's equal to RF sine theta. Oh, I started plugging in some numbers early, sorry. So 0.08 alpha is equal to radius of the wheel is 0.2. Force that's being exerted is the force of tension, 13.3 newtons. So then all of a sudden we can find our alpha. So 0.2 times 13.3 divided by 0.08. And again, this is just to get practice doing things this way, practice applying this net torque expression, because what if these two parts were switched? Then we would be doing the sum of the torque stuff instead of the sum of the forces stuff. So we get 33.25 radians per second squared. All right. Well, that is that problem there. Again, there's the faster way to do it, but then there was the angular acceleration way that we just wanted to get alpha by doing the net torque. So on a test, use the fast way, but this was just to get some practice with that net torque expression. All right, moving on to the next page and our last problem here. Okay. We have a disk rotates around its center of mass. I have a disk is 1/2 mr squared. It has a diameter of 40 centimeters and a mass of 250 grams. So I'm going to start drawing this over here. Disk rotates around its center. It has a diameter of 40 centimeters, so 0.4 meters, and it has a mass of 250 grams, so I'm going to say 0.25 kilograms. The disk begins at rest. Okay, omega naught equals 0. Right, and I did omega as opposed to v because it's a disk. Disks rotate. And then a force of 8 newtons is applied to the edge of the disk. So we've got a force of 8 newtons being applied to the edge of the disk. I guess I should rephrase this to say it's applied perpendicularly. Or maybe I should say tangentially. That would probably be even more clear. It's applied tangentially to the edge of that disk, which means it moves, it's applied along the edge of the disk. What's nice about that is that if we take a look here, that is perpendicular to our radius. So anytime we are doing this RF sine theta stuff, that sine theta goes away to 1. Okay, after 3 seconds, what is the angular velocity of the disk's rotation? So we're looking after 3 seconds, what's the angular velocity? After, what's the angular velocity? So we're looking for omega final. Well, we're given a force and we're given a time. Here is, right, forces and times, you're looking for velocities. That's where I have told you in the past to look at the conservation of momentum, but not quite the conservation, but the change in momentum of P naught plus or minus P, or the change in momentum, delta P, is equal to P final. It's just in this case, our thing isn't moving, so we can't use P. We have to instead use L. So what we'll say is L naught plus or minus the change in angular momentum is equal to the final angular momentum. So this is something that AP does not give you this. What they do give you, though, they give you that delta L is equal to torque times time. That's what they do give you. And they give you that angular momentum is equal to I omega. So you basically have to go from saying wherever it started, okay, here's our change. And since we started at rest, we can't go slower than rest. So I'm just going to say plus there. Here's our change. And now we can look at where are we finally. All right, so this is, and I hinted at this before when we learned about torques the first time, of now we can use torques to look at how things change their angular momentum, because what's the only way that we can change the angular momentum of an object is applying an external torque. So how do we mathematically calculate that? That's what we're looking at here. All right, Well, we've got our disk rotating around its center of mass. We're given mass and radius here. So since I see I popping up in a couple of places here, let's solve for I. So 1/2 mr squared, 1/2 mass is 0.25 kilograms, 1/2 0.25. So m, and then radius was 40 centimeters, so 0.4 meters, m r squared. And this is our I. Whenever you're doing these calculations, make sure you label them so you don't just have a random 1/2 times 0.25 times 0.4 squared, because otherwise a grader doesn't know what you're doing. A grader doesn't know the inner machinations of your mind. We can't see exactly what you're trying to do, so just label what variable you're looking for. All right, you plug that into your calculator and you get 0.02. So this rotational inertia of this disk, 0.02 kilogram meter squared. All right, and we can plug this in for our rotational inertias that we need in our change of angular momentum expression. So we have 0.02, and then it begins at rest, which is 0. Oh, okay, so this whole term actually goes away because it's multiplied by 0. Plus the torque, well, torque is RF sine theta. And we already kind of discussed that this sine theta will go away because the force that's being applied, if it's tangential to the disk, that is perpendicular, so that goes away. For some amount of time is that I, and then the omega final. Okay, so we can, let's plug in some numbers here. Well, the radius of our disk, or we're told diameter, oh shoot, I need to back up. My apologies, because up here I plugged in the diameter. Don't make my mistake here. Instead of the radius, which the radius would be half of the diameter, so 0.2 squared. So if we recalculate this, we get not 0.02 kilogram meter squared. We get 0.005 kilogram meter squared, and that's our rotational inertia of this disk. Okay, that just tells you be careful. All right, so R 0.2 when we're doing this radius of the disk, 0.2. And then, if my pen works, here we go. The force being applied is 8 newtons. That sine theta went away to 1 because it's perpendicular. This was applied for 3 seconds. Our F, and then there's our time, is equal to I, 0.005. And then omega, wow, I made a lot of mistakes here. That should not be omega squared. That should just be omega final. I am so sorry. So I, and then omega final. All right, well, we can get omega final then. Omega final is equal to, and we do 0.2 times 8 times 3 divided by 0.005. And I get a final angular velocity of 960 radians per second. And yes, that is a big number, but 1/4 kilogram is not a very large disk. So it'll be pretty easy to rotate it. If we're applying a constant force, that'll accelerate pretty well. Okay, well, a student performs the experiment above, but discovers that the final angular velocity after 3 seconds is 225 radians per second. Oh, but we expected 960. 225, that's really low. What's the most likely source of error? Well, if it's a student performing an experiment, that means that this is real life. And what did we assume? That's not true. Friction. Friction. So in some way, shape, or form, there is friction acting on the rotation. whether that's the disc sliding against something, or if that's the axle of the disc as it's moving around. Right? Because it has to spin around something. It can't just spin around nothing. So there's something that has to be held in place while the disc is not. So moving versus not moving, there will be friction somewhere. That's the most likely source of error that I would say. And number 2 of this part, determine the frictional torque acting on the disc. Okay, well, I want to take a quick peek at this expression that we set up above. Here, this I omega naught plus the torque times time is equal to I omega final. Now, when we only have one torque acting on our system, this is a pretty easy torque to figure out what do we do with. But now we have 2 torques. We have that torque applied from the 8 Newton force, and there's some sort of frictional torque that's acting on this rotation that's just slowing us down. Which frictional torque, and you can see right there, there's no implication. It says it outright. There is a frictional torque. So this torque here in our delta L, because remember this whole term came from being delta L. What this torque actually is, it's the net torque. The net torque times our time. Well, and in this situation, our net torque, well, we have our torque, and I'm just going to call it torque applied from the 8 Newton force minus that torque of friction. Now we have the torque applied minus the torque of friction. So that's our net torque. Well, we know this, we don't know this. Basically, what I'm going to do is I'm going to take this whole situation and find the net torque. Once we have that, we can use it, since we know our torque applied, we can use that to find our torque of friction. All right, so we know our omega initial is at rest, so there's nothing there. So now we'll say our net torque times our time is equal to our I omega final. Well, our net torque is now our unknown. We don't know this because the frictional torque is involved here. But our time is 3 seconds. They performed that experiment using 3 seconds. I, our rotational inertia of the disk, 0.005. Omega final, we are told, well, at part A, we calculated what we expected, but now we're told that they only get it up to 225 radians per second. So we can say that our net torque, the net torque that actually was applied on the disk, if we do a little bit of math here, we get net torque being 0.375. 0.375, remember units of torque, Newton meters. Newtons times meters. Which we can take over here. We know 0.375 is our net torque. Our applied torque was RF. Remember, the sine theta went away. So R is 0.2, F is 8, so we can say 1.6. And then minus our torque of friction. So our torque of friction that we have here, if we solve for this, 1.6 minus 0.375, and I get our torque of friction 1.225 newtons times meters. There's our frictional torque. Okay, so that'll do it for our class problems here. I hope it at least gives you a better understanding of how we might apply some of these some of the, like, net torque equals I alpha, how we might apply that into all of the places of things moving, of things accelerating, whether that's a disk, whether there's a string attached. Those are pretty much the ones that AP likes to do. All right, when you run into questions, let me know. Otherwise, I will see you next time.